going to do lecture today on 2910. 2910 is magnetic properties of matter. Of course, you need to learn this because, of course, this does matter. And yes, Bryson, that joke was for you. We are not doing 29.8 or 29.9. 29.8 was initially going to be done, so we won't. If you have any questions on 29.8, do not do them. You can't do wrong, but I'm not going to get accounted for credit. So we're going to finish up with 29.10. Of course, 29.9, I'd like to do it, but it's on electric motors. We're going to get on generators later on. And generators, just a motor run backwards. But I want to talk about, there's three basic properties of matter that show magnetism. And I want to talk about that. I do have black today, so hopefully you can see better. These magnetic properties of matter. So 29.10, magnetic properties of matter. Okay. Now, basically, these properties come down to atomic magnets, or basically atom is the key word there. Electron spin. I'll put that in quotes because it's not really spinning, but it acts like it is. And then we're going to look at ferromagnetism. Alright, with atomic magnets, basically I'm saying the atom itself is a magnet. And if you want to look at the old Bohr model of the atom, of course you have the nucleus here, you have the positives in the middle, that's like the sun, and going around it you had the electron, like that. That was the old hydrogen Bohr model of the atom. Now of course, this wasn't very interesting because it was, of course, boring, but okay, thank you for laughing. That was one of my better ones. But this Bohr model of the atom basically is going around and around and around and around and around. And so, right-hand rule, as this goes around, you're going to get a magnetic field coming out of the board. Excuse me, it would go into the board, so that's a negative charge. So it would be the opposite direction. But it would be into the board. So this atom goes around and acts like a magnet. Now, of course, you're saying that's 2D. That's not electron clouds. That's not the way they work, Knight. And I'm like, no, it's not, but it's good enough to explain it a little bit. Because what happens is, in an electron cloud, it's not always spherical. Some of them are a little elliptical. Some are a little funkadelic looking if you look at electron shells and stuff like that. So that they don't have symmetry in one direction. So if they have a preferred symmetry, so it's not just in one direction, but a little bit more in one way, a little less in another. If it's not nice and spherical, that's what I'm saying, then there's a residual effect of going around more in this direction than, say, going in that direction, or going around in the other direction. So these atoms themselves, the fact that electrons charge moving around a central spot, is creating a magnetic effect. So atoms act like magnets. And if you want to think about this is non-spherical shells can give a weak magnetic effect shown. Okay. And for a lot of metals, iron especially with ferromagnetism, that's a little, we're going to talk about something else there. You got loose electrons hanging out in the outer shell, they just kind of do what they want a little bit. These things tend to show a magnetic effect on their own. And they preferentially act more like a magnet than, say, like magnetic helium or something like that. You don't have a lot of that. Of course, things with shells, they're filled up, they kind of balance each other out. These things kind of cancel each other out, I should say. But atoms themselves act like magnets. Atoms act like magnets. So you can think of an atom itself as a magnet. Now, what about this electron spin? Well, electrons act like they're spinning. They look like they're doing this, right round, baby, right round. They act like they're spinning. And so the electron itself sit there and spun around. It's a moving charge. And that moving charge, in this way, it's up. Since it's a negative charge, it would go down. It would create a magnetic effect just from being there, just from sitting there spinning around on its own self. So the electron acts as if it is spinning by itself, like a top. Of course, for you newfangled kids and everything, a top was something that was an old-fashioned toy. You would take it, you sit it on the ground, you spin, wrap a little string around it, and you pull on it, and it would spin. And you sit on the ground, and it would sit down. Woo! So, fancy name was gyroscope. If you went to like a science place or something like that, but basically an old top is what they call it. And it would sit there and spin. Well, the electron acts as if it doing it because the electron itself has its own magnetic moment. In other words, it acts like a magnet itself. It doesn't really spin, we don't think. And the effect is quantum mechanical. So I'm not going to go over it anymore, but the electron spin, if you take modern physics, you take modern, if you take quantum, you'll get into electron spin. And this electron spin, the electron acts as if it's spinning, creates a magnetic effect itself. They tend to want to pair up. You have to take that into account with the nucleus. You understand how a nucleus works. Now, with ferromagnetism, ferro, of course, ferrous, iron, things that tend to have iron or material a lot like iron in them. And what we found is that these things have magnetic domains. And each of these, so inside a bar magnet, basically you have little I should say areas. From a 2D perspective, it's areas. From 3D, of course, it's a volumetric space. But you have these magnetic domains. And inside each of these magnetic domains, and these things may be 0.5 millimeter, 100 microns size or something like that, you have, say, a B field. Now, for this one, we're going to have the net B field is in this direction. Now, this one may be there, but this one may be a little bit here. This one may be a little bit here. This one may be a little bit there. That one may be there. Yeah. But when you sum them all up, I can go blah, 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 blah. So when you sum them all up, though, the net sum of all the domains, that creates a magnetic field in this direction. And that bulk effect is what we see. Now, are all those little domains going in one direction? No. They're kind of going around a little bit, but the net effect of summing them all up does. Gets a slight one in this direction. Now, you can say, well, how do they end up getting slightly in that direction? They get this way from magnetic field. So things that are rocks that are magnetically, act like magnets to begin with, these were known as lodestones. Not as the guy from Spaceballs, but lodestones. Now lodestones basically were magical and everything because they were like natural magnets. Now what happened was, as these iron would cool down, these rocks that had a lot of iron in them would cool down. The Earth's magnetic field that the Earth always has, as the Earth's magnetic field, what it does, it basically, these would tend to want to line up these magnetic domains. And some would line up more than the others. Now, if they cooled really slow, it can help them out. If they cooled really fast, it wouldn't have time to be able to move around these domains with these. And these are just, these domains, these groups are just groups of particles that kind of, and these, of course, atoms interacting with each other. But if it cooled down slowly and stuff, you could create, there would be rocks, basically, that acted like magnets. Weak magnets, but they acted like magnets. And they get this external magnetic field. This could be from the Earth. Or, if we want to create our own magnets, from a solenoid. And of course, a solenoid is just a coil of wire with current running through it. Just a coil of wire with current running through it. Now, why would you take a coil of wire with current running through it? Well, if you got a coil of wire, like this, and you're working on your car, because you actually have to do work on your car now that you're home and you can't go take it to everybody. You drop one of the nuts down into the motor. You're like, oh my gosh, I can't get it. How am I going to get down there? Well, if you had a magnet on a stick, you could get it. Well, how are you going to find this magnet on a stick? Well, you don't go to the store and ask for, can I have a magnet on a stick? Actually, there's auto parts place might have. They'll laugh at you, but then they'll go show you what to buy. But if you don't want to do that, you can take a screwdriver. And you take, actually a car battery works if you're smart about it, but be real careful. And you take a coil of wire, attach it to both real quickly, and have a screwdriver inside of that, or to like a 9-volt or something. And that current running through it will actually align the magnetic domains in your screwdriver. It will align them. As it aligns them up, it'll basically make that screwdriver a weak magnet. And if you can get it aligned well enough, what will happen is it'll go down in there, and you can pick them up. And that's really cool. Now the problem is, of course, if you work with electronics that has external magnetic fields can push electrons in places you don't want them. So how do you get rid of this effect from this bar magnet? How do you orient these magnetic domains in a random pattern? Beat it. Michael Jackson, that magnet, right? And if you do that to it, what you're going to do is the magnetic domains are like bounced around and everything, and so they'll get jangled around, and you'll weaken that magnetic effect in the screwdriver you have. And it works. It works pretty good. I've done that for some stuff. I've actually had to do that to retrieve nuts and bolts out of the my old Mustang. I used to fix it. So they get this way, and if you look in your book, I think I've pretty much finished most of that work. This is known, one thing I want to say that this is an induced magnetic dipole. It's an induced effect from an external field. It comes from an external field causing it to happen. Okay? That's an induced effect. And some things will stay there, and some things, what happens when you remove the field, they'll just go right back to how they were. Magnetic domain in a field, go back to how it was. Electromagnets or things like that. When you do an MRI, basically, some of you may have had MRIs, what happens, certain things in your body have varying, the magnetic domains in it kind of vary a little bit how much they turn. So if you apply a huge magnetic field to it, then you look to see how it changes from the induced magnetic domains inside it, you're actually seeing inside that, you can see inside there. A different material will react different, its magnetic domains will change differently. You know, your organs in there, not your piano organs, of course, but like your kidneys or your liver and stuff like that. You know, that will look differently. And if there's like a bad, tumor someplace, you'll see something, there'll be a change in the magnetic domain there really where it shouldn't be, or it'll be different whenever it becomes the density of the tissue or something like that. Okay? So MRIs use an induced magnetic dipole, and they kind of measure it, and what happens is when you let it go, when they get rid of it, it just goes back like it was. And certain materials, it's called paramagnetism and diamagnetism. Some stay that way more than others, and everything acts like a magnet at some level. And you can levitate a frog in a strong enough magnetic field. Haven't tried that in humans that I know of, but that would be pretty darn cool. That would probably push electrons in the brain, places it shouldn't go. But hallucinogenic effects.